As we said in the last video, the purpose of glycolysis is to make 2 ATP for each glucose and to do so very quickly. I also said that the first 5 reactions are an energy investment phase where we don't actually make ATP, but we lose it. So let's start in on the first 3 reactions, which are on the next page. Here's how we're going to do things. We're going to tell you a number of things about each reaction, and these are the things that I want you to know. The first thing we want to say is that the name of the enzyme for the first reaction is hexokinase, and that'll mean more a little bit later. But let's start right in with the substrate names and the product names. In this case, we're going to take glucose. Maybe this is glucose you've taken in your diet, or maybe it's from glycogen storage in your muscles or liver. And we're going to take an ATP as well and invest that ATP currency into the glucose by transferring a phosphate from the ATP to make glucose 6-phosphate. So let's make sure we get those names down. Glucose 6-phosphate, and the other product is ADP. Now this reaction is easy because we've already done it in the past. Okay, let's pause for a second and see if you can remember a few things from our introduction chapter earlier. First of all, which of the 6 types of reactions is this? Second of all, what are we making and what are we breaking? Let's pause for a moment and see if you can come up with those things. Okay, the first thing we're going to do is below the enzyme name, we're going to put which of the 6 types of reactions this is, and it's a group transfer. You can remember that because we are transferring a phosphate group from ATP to another molecule, in this case to glucose. Next, what are we making and what are we breaking? We're breaking a PA right there, and we are creating a PE. And we can put this down over here as important chemistry that we need to know about this reaction. Breaking a phosphoanhydride drives formation of phosphoester. Remember, this is a coupled reaction. The negative 30 kilojoules per mole that we get from breaking the anhydride, phosphoanhydride, is enough to drive the formation of the phosphoester at positive 15 kilojoules per mole. One last thing before we move on. We're going to keep track of our investment. We've lost an ATP instead of our goal, which is to gain one. So we're going to put down that this is a -1. We're in debt for ATP. And we're going to keep track of that in that little box there. Okay, moving on to our second reaction. Reaction number 2 is we're going to take glucose 6-phosphate, which we just made, and we are going to make it into fructose 6-phosphate. This is an isomerization. You probably could have guessed that from the name of the enzyme, which is phosphoglucoisomerase. And that is chemistry we have seen before as well. Now what's interesting about this is that in order to do a isomerization like this, we have to linearize glucose 6-phosphate. We can do that because the anomeric alcohol over here is uncapped. It can linearize, and it does so in the enzyme, and then we undergo a isomerization. Let's test you on that one. What is the type of isomerization to go from here, from glucose to fructose, and go ahead and draw out the structure that we would expect for that type of isomerization. Give it a go. Okay, this is a aldehyde-keto isomerization, and we did that a lot back in our sugar chapter. And we're going to go ahead and point out that for such an isomerization, we have to switch the aldehyde carbonyl from carbon number 1 to a ketone carbonyl on carbon number 2. That's the swap we make there, and when we do so, the sugar can recyclize and form cyclic fructose 6-phosphate, the product. Now, At this point, we just need to say a little bit about the chemistry, and all we need to say here is that it's an aldoketo isomerization. That's the chemistry you need to know. We've already seen that in the past. Have we lost any ATP on this? Have we gained any ATP on this? The answer to both of those is no. So we're keeping a running total. We're still in debt 1 ATP, but it hasn't gotten any worse. Okay, we're going to take fructose 6-phosphate in reaction number 3, and we're going to go ahead and essentially do something very similar to what we did in reaction number 1. We are going to take fructose 6-phosphate, and we are going to make it into fructose 1,6-bis-phosphate. And to do that, we're going to put another phosphate on to the first position. Thus, the name of this is fructose 1,6-bis-phosphate. Bis means 2, but bis means 2 in the sense that you have 2 phosphates attached on separate parts, unlike diphosphate, which means you have 2 phosphates attached together. Now, to put a phosphate on there, you might be able to guess that we need an energy source, and we're going to use an energy currency, ADP. We're going to donate a phosphate, and it's going to drive it on to the first position. So we can ask you again, which of the 6 types of reactions? Well, this is another group transfer. And that is essentially identical to what we did before. We can say a PA breaking, that is negative 30 kilojoules per mole, phosphine hydride breaking, drives 15 kilojoule per mole phosphoester formation. This is almost identical in every way to reaction number 1. They're both done by kinases. To finish this off, all we need to do is say we are now doubly invested of ATP, and we're in debt 2 ATP, so we're at negative 2. Now, before we put this video to rest, I want to go on to a later page and make a point. If you jump way out after all the reactions are done, I've got 5 different types of enzymes here, and it's time for us to define one of these very carefully. A kinase, of which we saw 2 in the first 3 reactions, reaction 1 and reaction 3. One was hexokinase, the other was phosphofructokinase. These are classic enzymes. And what we can say is this is an enzyme that transfers a phosphate from a nucleotide triphosphate, almost always ATP, but it could be other things too. Transfers a phosphate from ATP to another molecule. That's exactly what we saw happen. You're going to use the phosphine hydride energy that's released when you break that bond, and you're going to use that energy to drive it on and form a phosphate bond to something else. So kinase is a critical enzyme in not just biochemistry, but of all of biology. There's some 600 kinases in the human body, and they all do this very similar chemistry. So we'll leave it at that for now and return in a new video for the next 2 reactions.